Orban Radio, Television, and Internet Audio Processing webinar. I'm Jane Rush, Sales Director for CommSmart Canada, and we are a manufacturer's representative of Orban Labs. Today's webinar will consist of a 50-minute presentation delivered by Bob Orban, the founder, VP of Engineering, and the inventor of the popular Optimod processors. Following Bob's presentation, we will have a 15-minute question and answer period. We encourage our attendees to file question requests by clicking on the green hand, which will appear below the video screen. After you click a request, you will then receive a message on your device asking for permission to enable your audio. By clicking yes, your microphone will then be turned on and everyone will be able to hear you. Now, should you wish to be seen, you can easily enable your video camera. After your question is asked, we will disable your microphone and move on to the next attendee's question. This entire presentation will be recorded, and following the webinar, I will send you a link where you have an opportunity to view it again or to share it with your colleagues. Now, on behalf of CommSmart Canada, I thank you for joining us today to learn from one of the world's experts in audio processing. Now,
hi everybody. Thank you for joining us this afternoon or this morning, depending on your time zone. So I'm going to mute my camera here and with the presentation. Okay, so I'm going to be talking about audio processing for radio and digital media, good practices and some pitfalls. The old question, why process? For digital radio and netcasts, it creates a consistent polished sound, a signature sound that's part of a transmission's overall branding, helps compensate for imperfect production, careless operators, creates an appropriate balance between speech and music, and except for increasing coverage, processing for digital radio and the internet have the same goals as processing for analog radio. Processing for digital radio and netcasts, the main difference between optimum processing for analog and digital radio is the peak limiter technology. To optimize lossy codec performance, the processor should add as little additional spectrum to the input signal as possible. This implies use of non-clipping limiters using look-ahead techniques because clippers add a lot of extra distortion products that the codec then has to encode. Processing for low bit rate. Today's MPEG-4 standard low bit rate codecs such as HEAAC, HEAAC-V2, and the new universal XHEAAC use spectral band replication, which is a bandwidth extension technique. The codec uses straight AAC encoding below a specified crossover frequency, which depends on the bit rate. Above the crossover frequency, the receiver generates plausible high frequencies by frequency doubling lower frequency energy. The encoder sends a multi-band gain control signal to match the high frequency energy generated by the receiver to the amount of high frequency energy in the original audio as much as possible. How do you process for it? Because most of the problems occur at frequencies above 8 kilohertz, which is where SBR is active. The more neutral the HF balance, the less SBR is stressed. Don't use the audio processor to exaggerate high frequencies unnaturally. Perform high frequency limiting on overcooked source material, and don't let the processor increase high frequency density beyond that present in the source material. Other than that, process freely to achieve your artistic goals. AAC, which handles everything except the very highest frequencies, is in fact a very good codec. Another important issue that seems simple but really isn't is setting peak output levels in digital media. Be sure your peak limiter is so-called 0 dB FS plus aware, also known as true peak aware. This means that it anticipates and compensates for the effect of the analog reconstruction filter after a player's stack. This filter can cause levels that are up to 3 dB higher than the highest digital sample. And a example of this is a sine wave at 1/4 the sample frequency. If the phase is unlucky enough so that the sample points are at the 45-degree points on the wave, that's actually 3 dB lower than the peak level of the sine wave. A 0 dBFS plus aware peak limiter uses an oversampled side chain so that it will produce additional gain reduction if needed to quash analog domain overshoots. Because it removes program energy, the HEAAC codec can cause peak overshoots of 2 dB or more, and this is above and beyond the 0 dBFS plus effect. Additionally, some player devices will hard clip overshoots, even in their either in their digital or analog circuitry. Others will activate a questionable peak limiter, and Windows, I'm looking at you, to protect against hard clipping. So the recommendation is use a 0 dBFS plus aware limiter and set its peak output level to -5 dBFS. Any clipping that remains will have a low duty cycle and won't be heard. Another important processing topic is what to do about bass. Bass is important, but it must never be allowed to damage the mid-range. Many listeners don't hear bass, either because their radios are played quietly or because their radios can't effectively reproduce bass at any volume level. Even upmarket table radios like those from Bose, Cambridge, Polk Boston Acoustics, and others have little response below 70 Hertz. So for the mass audience, the mid-bass is more important than the bottom 2 octaves. Choose whether to emphasize mid-bass or low-bass performance based on your target audience and the radios they're likely to be using, speakers or earbuds. Speakers rarely have good response below 70 Hertz, except in very premium sound systems, but earbuds can go down to 30 if they're well sealed. Use processing techniques like bass pre-limiting that ensure that bass is not allowed to damage mid-range. And you can add a tasteful amount of soft clipping to the low bass so that it produces extra mid-bass energy for small speakers. And the Orban Optimods have had this feature in the form of the bass clipper ever since the days of the 8200 or even earlier, back to the 8100 actually. Another aspect of bass processing is subharmonic synthesis. This is an old bass enhancement technique originally popularized by DBX in the 1970s that has attracted some recent interest from broadcasters, but it has many pitfalls and snares of its own. It can help some older material with little energy below 70 to 80 Hertz, but never forget the equal loudness curves. Material below 50 Hertz takes up lots of peak level to produce significant loudness. So we look at the 50 Hertz line on this curve, and we see that it takes almost 40 dB SPL to have any audible sound at all at 50 Hertz, and that increases rapidly so that at 50 Hertz you're at over 70 dB SPL just to produce audibility. Moreover, close spacing of the curves means small changes in amplitude lead to large changes in subharmonic loudness. So you can see that the curves down here at 20 Hertz are extremely tightly bunched together compared to at 3 kilohertz where the ear is most sensitive. Because of the amount of peak level they use up, subharmonics will always make a broadcast sound quieter for a given amount of processing artifacts and or distortion. They use up peak level that otherwise could be dedicated to audio to which the ear is more sensitive, and this is an inevitable effect of the equal loudness curves. So, subharmonic synthesis is safest when created in the production studio, where the effect can be monitored by humans before it's let loose on the air. If you do put it online, it should be defeated automatically when the program material already has sufficient bass. Use it in conjunction with high compression ratio multiband compression to ensure consistent loudness of the subharmonics. Use bass IM distortion reduction techniques in the on-air compressor and peak limiter. Subharmonics should track the level of their generating frequencies in a frequency-dependent way to keep the amount of low-frequency enhancers subjectively constant. Moreover, subharmonics make male voice sound very weird indeed. So a subharmonic synthesizer should be used in conjunction with automatic speech music detection and should not be applied indiscriminately to material above 90 Hertz. Another hot topic of the last couple of years is declipping. Information is 100% lost in flat-topped areas and can't be recovered. A flat-topped waveform is a mathematical singularity. Recovering it would require dividing by 0, and as we all know, you can't get away with doing that because you get an infinity. So, declippers have to make educated guesses about what's missing based on interpolation from material surrounding the clipped samples. The interpolation has to use a model of the clipping process. But there's a gotcha. Many waveforms that actually look like they've been hard clipped have in fact been peak limited by more complex limiting processes with side chains in memory. Each limiter manufacturer has a proprietary way of computing the side chain, and for competitive reasons, these are seldom made public. Even if the side chain is public knowledge, if the compression ratio is infinite, then it's still impossible to deduce what the limiter's input was. So I'm going to show you a few pictures in the next couple of slides. First is a 5-minute waveform that looks like it's ridiculously clipped. Not counting the intro and fade out, its BS1770 integrated loudness is about -6.7 LUFS, and any declipper would work very hard to try to declip it. Based on the waveform, one would think that it has to sound awful. Yet, in fact, it sounds fine and doesn't sound distorted. And there it is. Looks like a newly mown lawn. And you can actually download this particular example from the Orban website. It is in the product section under the Optimod PCN 1600. And then if you go to the right of the page and click on the mastering, you'll be able to get these examples. So as far as this waveform goes, let's look at it a little bit more closely. Zooming into a 2-second segment, still looks ugly and clipped, but maybe not quite so much. So let's zoom in some more to the sample level. Okay, well, not so fast. In fact, this waveform was made with a very complex distortion canceling peak limiter, specifically the MX limiter in our Optimod PCN processor. That limiter uses a psychoacoustic model to minimize audible IM distortion. There's almost no actual clipping, and what there is has a very low duty cycle. In fact, the only place where you see 2 clipped samples in a row is right here, and because it's only 2 samples, you would never hear that as being distorted. Yet the declippers I've tested misidentified hundreds of peaks as being clipped and tried to fix them. Declippers can increase punch on transients by increasing peak levels by guessing what the missing waveform is. But this is not the same as canceling IM distortion. Distortion cancellation depends on having a precise invertible model of the peak limiting process, and this is usually impossible. Because declipping is a nonlinear process, it can make its own IM distortion that adds to any IM distortion present in the original track. The better the original peak limiting algorithm, the more likely it is that declipping will add IM distortion and not cancel it. So, the takeaways. If simple P-clipping was used on a given track, then declippers can help, but sometimes they make things worse. Therefore, the proper place for a declipper is in the production studio, so that human ears can determine if the declipper is helping or adding another layer of distortion. Moreover, in the broadcast processing chain, declipped waveforms force the on-air processor's peak limiter to work harder, so use declippers with care. Another interesting topic is phase skew correction. As we all know, the time delay between identical audio components in the left and right channels can cause comb filtering in the mono sum. This will cause high-frequency roll-off and, in extreme cases, a flanging sound caused by comb filtering with notches throughout the audible spectrum. Those of you old enough to remember stereo cart machines remember this as a huge problem back in the day. This is particularly important in FM broadcast, where auto radios often blend partially or completely to mono. In FM, phase skew errors cause the energy in the stereo subchannel to increase, which increases susceptibility to multipath distortion. Phase skew correction is also important in low bitrate streaming. So-called parametric stereo works by encoding the mono sum along with a low bitrate steering signal. This process is most efficient when there are no phase skew errors. HEAAC V2 and XHEAAC both use parametric stereo. Various phase skew correctors can have dramatically different performance and capabilities. Many correctors work by adding a simple time delay to the earlier channel. This models analog tape gap skew, but it can't correct multiple delay errors. For example, a recording could have both analog tape gap skew and comb filtering caused by two microphones picking up the same instrument in the recording studio. The simple time delay-based phase skew corrector can't fix this problem. Our multipath mitigator phase corrector is multidimensional. It can fix multiple unequal delay errors in a recording. It transforms the source to so-called intensity stereo, also known as Blumline stereo, maintaining full stereo separation while removing phase shifts between elements common to the left and right channels. To illustrate this ability, I created a 10-tone test stereo waveform with a 90-degree phase difference between each tone in the left and right channels. The power in the two channels is the same. The 90-degree phase shift produces a different differential time delay for each tone. Each time the frequency is halved, the delay doubles. So here's a spectrum photo of the test signals. It goes all the way from 250 to 9250 hertz in 1000 hertz increments. When you look at this as an XY display, it makes a very interesting Lycidas pattern. So what happens when you put the multipath mitigator phase corrector in line? Well, it puts all 10 tones in phase. Additionally, it has a crossover frequency control so that users can control the frequency above which the phase corrector is active. Using a 800 Hz crossover frequency preserves subjective envelopment caused by phase differences in the bass and lower mid-range, while still correcting problems in the range where comb filtering is likely to occur. On the other hand, using a lower crossover frequency may be better in FM broadcast if reducing multipath distortion is more important than envelopment. This depends on the terrain in the station's market area. So obviously, if you're in mountainous terrain, you need all the help you can get with multipath mitigation. If you're in the flat plains of the Midwest, it's much less of a problem. So I'm going to spend some time now looking at loudness control for both digital television, and digital radio. And I'm not only going to talk about the internationally standardized BS 1770, but also the Jones and Torek algorithm, also known as the CBS loudness meter and loudness controller. Subjective loudness metering and automatic online loudness control have a long history. The first online automatic loudness control technology was developed at CBS Labs in the mid-1960s in response to a Federal Communications Commission study regarding audience complaints about objectionably loud commercials. Bronwyn Jones and Emil Torek at CBS Technology Center revisited this work in 1980 to improve loudness meter accuracy, and this work was published in the SMPTE Journal. In 1983, the FCC Office of Science and Technology tested the J&T loudness controller, concluding that it was likely to reduce complaints caused by loud commercials. In 2005, Orban made substantial improvements to the J&T loudness controller gain control sidechain to improve smoothness, make the operation more audibly subtle, and produce more consistent dialogue loudness, even when dialogue is mixed with music and/or effects. So we've seen this picture before, but it's also very relevant to how you make a loudness meter. Frequency dependence is the primary element in loudness metering. The ear's perception of loudness is strongly dependent on frequency and varies literally over an AdB range between 3 kilohertz and 20 hertz. But there are other psychoacoustic issues that really need to be taken into account as well. One is loudness summation. And what that means is for a given total sound power, the sound becomes subjectively louder as the power is spread over a larger number of psychoacoustic critical bands, which are about 1/3 octave except in the very low bass. And another issue is loudness integration over time. A given amount of acoustic power sounds progressively louder until its duration exceeds about 200 milliseconds, at which point no further loudness increase is heard. The BS 1770 meter takes only frequency dependence into account. It's a wideband time-integrated power meter preceded by a frequency weighting filter, the so-called K-weighting filter. It uses gating to ignore low amplitude parts of the audio that don't contribute significantly to loudness perception. But the BS 1770 meter doesn't model loudness summation or the short-term loudness integration time constants of human hearing. And as a result, we see that it disagrees with human listeners by up to 6 dB. This is a diagram taken right from the BS 1770 standard itself. It compares the loudness as perceived by human listeners with the meter reading. And you can see there are a couple of outliers here that are 5 to 6 dB away from the center line here. And to maintain a +2 to -5 dB comfort zone, the straight line actually needs to be shifted downward slightly so that the meter underreads a significant amount of program material. And we'll see that this has caused some problems. Mechanically relying on the 1770 meter has caused complaints in the Hollywood production community. For example, here's one I found with an internet search. Quote, I did a -24 piece for Fox that was wall-to-wall singing and music for 2 minutes. Because of the overall loudness and continued full audio signal, I had to bring it down. And when it aired, it was 3 dB too quiet, even though it matched the magic LKFS number. I have no problem using these meters or meeting specs, but they're faulty. And as we'll see a little bit later, the AES finally recognized this in late 2015 and introduced the concept of genre for the first time to be 1770 meters. But meanwhile, let's talk about the J&T loudness meter technology. In terms of its psychoacoustic model, to deal with loudness summation, the meter first divides the signal into 8 frequency bands and applies each band to a rectifier followed by fast averaging, which mimics the so-called instantaneous loudness integration time of human hearing. For frequency dependence, the average outputs of the bands are summed with unequal gains that mimic the frequency dependence of the ear, as determined by experiments with listeners using octave band noise heard on loudspeakers in a room typical of a home listening environment. For loudness integration in time, the sum of the smoothing filter outputs is applied to a filter with an integration time of approximately 200 milliseconds. This makes the Jones and Toric a short-term or momentary loudness meter. So those are the 8 filter banks in the meter, and you can see that when they're summed together, they are approximately the inverse of the 70 phone equal loudness curves that we saw in an earlier slide. Loudness meter accuracy is limited by sort of laws of physics issues. For one thing, it's inherently limited by the fact that human listeners disagree by several dB when asked to match the loudness of test program material with a reference tone or wideband noise. Different people perceive loudness differently. A loudness meter can only be calibrated for a fixed acoustic listening level because the equal loudness curves show the ear's sensitivity as a function of frequency to be level dependent. The room acoustics and frequency response at the receiver are unpredictable, particularly at bass frequencies. Fortunately, bass doesn't contribute as much to the impression of loudness as the mid-range because of the equal loudness curves as we saw earlier. So this is not as difficult a problem as it might otherwise be. But these issues mean that automatic loudness measurement and control for broadcast will always be approximate. However, it's still important to minimize the average error by choosing a loudness meter that exhibits good correlation to the average loudness as perceived by many listeners in aggregate. So how do you make an automatic loudness controller? Automatic online loudness control has to start with an objective reference, a loudness meter whose indications closely match subjective loudness as perceived by listeners. The listeners being tested should match the typical demographics of television viewers, or in the case of digital radio listeners in age and gender. Both the 1770 and J&T meters have been tested in this manner. As we saw earlier, the 1770 meter exhibited a worst-case disagreement of more than 5 dB with listeners. The J&T meter exhibited a worst-case disagreement of 3 dB with listeners, although a smaller set of program items was tested. To make an automatic loudness controller, one can insert a loudness meter into a gain control computer sidechain, where the sidechain produces gain reduction that's the inverse of the loudness meter's output above a preset threshold. This topology is similar to a compressor, except that the loudness meter is used instead of a simple RMS or weighted peak detector. There are also program context limitations. An automatic loudness controller operates with reference to an absolute subjective loudness threshold that doesn't adapt to program context as well as a human mixer. For example, if there's a transition between very quiet program material, such as footfalls through rustling leaves or quiet underscoring, and a commercial, the commercial may still seem offensively loud, even though the loudness controller is controlling its loudness correctly with reference to other sounds that reach full-scale loudness. For this reason, mixers have learned to begin and end program elements with so-called bumpers that are intended to be at the same loudness as the previous or succeeding commercials and other non-program material. While automatic speech and non-speech discrimination can help a loudness controller understand context, it can't deal with all situations, like the examples above, where the adjacent elements are both non-speech. So, how do you make a loudness control system for online use in radio or television? We found that two-band compression doesn't control loudness well enough to avoid viewer annoyance in TV audio. If you combine two-band compression with loudness control at the back end, this produces loudness control that mostly preserves the spectral balance of the input. But at Orban, we prefer a system that consists of an AGC, 5-band compression, and loudness control. We find this most effective, and it prevents audible gain pumping caused by spectral gain intermodulation because of the 5-band compression. Spectral gain intermodulation is nothing more than energy in one part of the audio spectrum pumping elements in other parts, the classic example being a wide band compressor where bass pumps mid-range instruments up and down. So, in more detail, what does that back-end loudness controller block look like? Well, the Jones and Torek loudness controller can be combined with what we call the BS1770 safety limiter. Located after the J&T loudness controller, the 1770 safety limiter constrains the reading of the 1770 meter to a preset threshold, which we allow you to adjust 0 to +6 with respect to the target loudness, which in digital television is also the dial norm metadata. The limiter's 10-second attack time minimizes but can't eliminate loudness ducking on material with low peak to RMS ratio. Loudness ducking is an inevitable side effect of relying on the 1770 algorithm to estimate the loudness of such material. The limiter's 3-second release time prevents dialogue from following a loud commercial from being too loud, from being too quiet for an annoying length of time. The limiter's asymmetrical attack and release times can sometimes cause the 1770 meter indication to overshoot. However, using symmetrical attack and release times would be perceptually inferior. When the J&T loudness controller is placed before the 1770 limiter, the J&T controller prevents the 1770 controller from unnaturally increasing the level of unadorned dialogue. This is because the J&T controller locks onto dialogue better than 1770, particularly when the dialogue is mixed with music and/or effects. We found that an inverse 1770 gain reduction sounds unnatural when used by itself. It will subtly modulate dialogue levels when underscoring or effects appear behind the dialogue. And highly produced material with low peak to RMS ratio will be quieter than dialogue. So a recommendation is this: use a 1770 safety limiter if controlling overall loudness is more important than achieving the best subjective source-to-source consistency of the anchor element, which is usually dialogue. Otherwise, use the J&T loudness controller alone. So here are some measurements that compare the loudness control with the BS1770 safety limiter off and on. These are histograms, and a histogram is just the probability that the loudness will fall within a given range for a certain time sample. And I believe the ranges here are 1/10 of a dB. And the meter that was used for these first two pictures is a BS1770-2 meter. we can see that with the safety limiter off, the loudness is centered around -24, but there is one outlier here above -22, and then there's another one here at about -22.5. So turning on the safety limiter gets rid of the one at -21.5 altogether, and greatly reduces what occurs here between -22 and -23. So let's look at the same thing, but with the Jones and Toric meter instead. And this is sort of interesting. With the BS1770 limiter off, we see some outliers up here. But at the same time, when we turn it on, we also see outliers, and this is because the Jones and Toric meter uses a different psychoacoustic model. So, what can go wrong? If not optimally designed, online loudness controllers can introduce objectionable audible artifacts. And I've heard a lot of this on the air with digital television lately. Spitty dialogue with hollowed out range caused by inappropriately designed multiband compression. Ambience pumping and breathing caused by poor or no silence gating in the compressor, which ironically was a problem first solved in 1959 by the CBS Labs Automax. Stereo image shifts caused by unsophisticated gain coupling between audio channels, and slow pumping of loudness caused by using loudness meter time constants in a loudness controller sidechain. Mechanical reliance on the 1770 meter can cause inconsistent loudness between program segments, although the inconsistency usually doesn't exceed 3 LK. While this is within the +2 -5 LK comfort zone defined in ATSC A85, it can nevertheless give the impression that the broadcast is sloppily produced. So I'm going to talk about loudness normalization in the context of streaming and digital radio. Here there's no noise penalty for lowering average modulation. Compared to analog FM, a much stronger argument can be made in favor of loudness normalization. However, loudness normalization must be done in a subjectively benign way. The 1770 meter penalizes formats specializing in music like dance, techno, etc. that was highly dynamically compressed in production, and it can easily overindicate the loudness of such material by 3 dB compared to the subjective impression of human listeners. If the 1770 meter is relied upon to balance the music and announcers or presenters, this can cause the announcers to be substantially louder than the music. For some formats, short-term inverse 1770 loudness control simply sounds wrong, sucking the impact out of music and causing weird sounding shifts in loudness between sources. Fortunately, the AES recommendation for loudness of audio streaming and network file playback issued in the fall of 2015 takes genre into account for the first time in the context of VS 1770. And let me quote from the recommendation. Within a given program, the largest perceived difference to be noted is speech versus music. Speech normalized to the same integrated loudness as a music stream inevitably sounds too loud. It is recommended to normalize speech, that is to say dialogue segments, within other segments 2 to 4 LU or more below the loudness of the other segments. Moreover, modern radio-style audio processors have been crafted to achieve subjectively pleasing loudness balances between sources. They don't require extra 1770-based loudness control, which I believe does more harm than good. On the other hand, Setting a static, very long-term 1770 target loudness for a given transmission can often be useful and is much better than doing nothing at all. But at most, I believe that 1770 should be used to set the static output level of the audio processor, not to adjust loudness between sources without considering genre. Another potential problem is setting the target loudness too low. iDevices, iPhones, iPads, etc. Typically can't achieve satisfying levels into typical earbuds when the target loudness is minus 23 LUFS. There's not enough gain available. Player devices often have built-in peak limiters of unpredictable quality, so it's unwise to stream material having an extremely high peak to average ratio that can trigger these limiters. A good compromise is minus 16 LUFS, which allows a satisfying listening level and is still capable of very high subjective quality. The AS streaming loudness recommendation specifies a target loudness of minus 16 to minus 20, with the minus 20 being more appropriate for fine arts programming, particularly classical music. Although even classical music, you've got to watch out that the peaks aren't going to trigger the limiters in the playback device. So we recommend that the transmission processor, not the player device, do that peak limiting. The AS recommendation advises setting the peak limiter threshold to minus 1 dB true peak, which is the same as 0D FS plus. We believe that minus 1.5 dB true peak is more appropriate for netcasters using the HEAAC-V2 codec at very low bit rates like 32 kilobits per second. So I'm going to show you some measurements. Modern radio-style audio processing achieves satisfactory source-to-source consistency without need for extra loudness control. Orban processors take genre into account automatically and have automatic speech-music discriminators. In our experience, the J&T loudness meter takes genre into account better than 1770, so the J&T meter can be used to guide loudness balances between genres without needing the correction offsets that the AS recommendation specifies. Source of the measurements was a 17-minute recording from the program line of KBIG Los Angeles, with most of the music edited out. The recording consists of a wide variety of material, including male and female voice, spots, promos, a traffic report from an aircraft, and some music. The audio processor was an Optimod FM 8500 running the Loud Hot preset. And the first plot I'm going to show you is loudness versus time, using the second generation J&T loudness meter as the measuring device. So, over the course of this segment, we see that the loudness is really very well controlled. Seems to be within a 0 to minus 3 dB window most of the time, except it drops here at this segment. And this was the traffic report from the helicopter. It was one of those typical, carbon mic, highly distorted, noisy, bandwidth limited pieces of audio that we found actually sounds better balanced with the high quality audio if it comes out at about minus 3 dB as measured on the Jones and Torg loudness meter. And here's the histogram of that same segment. Again, we can see that the loudness is controlled typically very tightly in a plus or minus 2 dB window, and even the outliers here are slightly below plus 2 and above minus 4 are still well within the plus 2 minus 5 dB comfort zone. So, what are the takeaways of the loudness discussion? Take ATSC 885's prime directive seriously. Quote, because loudness is a subjective phenomenon, human hearing is the best judge of loudness, end quote. Relying solely on BS 1770 without listening is a recipe for substandard source-to-source consistency. Dense, highly dynamically compressed material will often be more than 3 LK quieter than unadorned dialogue. Dialogue levels will vary depending on the amount of underscoring and/or effects in the track. The J&T loudness meter and loudness controllers based on it tend to lock onto dialogue. The BS 1770 meter indicates the approximate overall loudness of the program, although it tends to overread material with a low peak to RMS ratio, so it's necessary to take genre into account. If dialogue levels are held constant, the 1770 meter will indicate that dialogue mixed with underscoring and effects is louder than unadorned dialogue, even though the dialogue levels themselves haven't changed. The 1770 short-term measurement, which is an ungated measurement with a 3-second integration time, is particularly prone to this behavior and should not be used as the sole reference for an automatic loudness controller. Automatic loudness control is unlikely to ever be good as a human mixer when the most aesthetically pleasing results are desired. Only humans can understand the subtleties of context. Cascading a J&T loudness controller and a BS 1770 overshoot limiter is often a good compromise. The J&T controller prevents unadorned dialogue from being unnaturally pumped up in loudness, while the BS 1770 controller catches material whose overall loudness might be considered excessive depending on the loudness control philosophy of the broadcaster. And I haven't talked about file-based loudness control yet in this talk. All that is you have a piece of software that goes through your playout system and makes a BS 1770 integrated loudness measurement of each piece of program material in the playout system, and then either adjusts the target loudness metadata or actually adjusts the loudness of the audio itself in order to make it hit the target loudness. However, this is more likely than online loudness control to create loudness inconsistencies at the boundaries between program elements, because obviously when you loudness normalize each piece of program material, it doesn't know about transitions. In digital transmission channels, static loudness normalization using 1770 is much better than doing nothing at all. Minus 16 LUFS matches current popular players better than minus 23. The AES recommendation recommends target loudness of minus 16 to minus 20. Modern radio-style processors provide satisfactory source-to-source consistency without needing additional dynamic loudness control. And all receivers have loudness controls, and all listeners know how to use them. Providers of program streams via digital media should be strongly encouraged to statically normalize the loudness of their transmissions to make them consistent with others. If providers are not using online audio processing, then it becomes necessary to normalize each program element before playout. But strict normalization to 1770 will penalize some program elements, formats, and styles of processing by making them subjectively quieter than the media's target loudness. So take genre into account per the AES recommendation and trust your ears if they disagree with the meter. So I'm going to talk about an interesting product that we have. This is Optimod PCN 1600. It's our first software-only audio processor. It runs natively on Intel processors and Windows PCs. And unlike our PCN 1101 card. It doesn't use any co-processing. It actually uses the Intel CPU's processor for all of the audio processing. So this is in fact our most advanced streaming and mastering processor. It has some features that have not yet made their way into the Orban hardware processors. All of the processing features of our Optimod PC 1101 plus more. It supports modern target loudness concepts, and you can actually set the target loudness here on the Less More tab, and it's EBU R128 and ATSC A85 aware as a result of this. It has built-in BS1770 and Jones and Toric automatic loudness controllers, as we talked about earlier, put in the recommended cascade. Easy Less More adjustment of processing presets. We have seen this in Orban processors ever since the days of Optimod FM 8200. Pass-through mode allows you to smoothly bypass the processing with a delay matched crossfade, and you can adjust the pass-through gain according to your needs. This is particularly useful if you are in a network situation and have program material in your ingest that your provider says is already correctly loudness controlled, and the provider doesn't want you to do any further processing with it. It has a built-in phase skew corrector, and this is our multipath mitigator, as described earlier in this talk. Our MX peak limiter, which is applied in a processor for channels without preemphasis for the first time in an Orban processor, adds crispness and punchiness even in processing loudness. There's a built-in Optimix, which is a stereo to surround upmixer, and this creates instant surround from stereo or even mono. So you can use this in conjunction with MPEG for parametric surround. The way parametric surround works is that it actually encodes a stereo mixdown of the surround signals, and then in addition to that there is a low bit rate steering signal that allows the player device to reconstruct the surround channels in a very convincing way. So it is basically an extension of the idea of MPEG parametric stereo. Mono bass and steep slope crossovers are available to let you customize bass like never before. Program adaptive subharmonic synthesis adds bottom and punch to old recordings, and we've built in intelligence, as I discussed earlier, so that it doesn't work on voice and keeps things sounding natural. And this is another new feature for Orban processors, parallel compression. What parallel compression is where you take the output of the multiband compressor and you add the input to it so that the input is passed through to the output of the processor. And then you take down the threshold of compression quite a bit compared to where you would normally operate the compressor. So what happens is that when the program material is quite quiet, the multiband compressor does very little compression, so it contributes quite a bit to the level at the output. But then as the low gets higher, the multiband compressor takes more and more gain reduction, and it contributes less and less to the output compared to the input feed-through path. So The effect of this is that it subtly amplifies quiet material without affecting the punch of loud material. It can be very useful as a preprocessor ahead of Optimat FM for almost any format. It's particularly effective for classical music, but it's also useful for other program formats as well. And when you combine that with the fact that the subharmonic synthesizer and multipath mitigator phase corrector are also available, it makes this piece of software an attractive preprocessor for older Optimat FMs. So here's a picture of the input versus output curves of multiband compression. This is as a function of so-called knee controls in the 1600 PCN. And you can see that most of the action happens here at the very low levels. And then the compression ratios basically get closer to a one compression ratio as the level increases, and by the time you get up here, it's almost 1-to-1. Okay, I'm going to mute my cough switch here. All right, hopefully I'm back. Okay, so as far as output goes, this uses standard Windows MME and Wasabi Audio L. It's compatible with most sound cards. If it shows up in the Windows sound control panel, it will work. And with third-party drivers, it supports AES-67 compliant audio over IP connections. USB key authorization makes it easy to move processors between main and backup computers. The processors move with the key, and no internet connection or reauthorization is required. So you can install the software on backup computers and have them all ready to go. And if your main computer goes down, all you have to do is move the key over and you're back in business. Architecturally, the way the software works is that the audio processing itself runs as a Windows service. So it automatically starts on the server machine. And then you communicate with it using an application that is very similar to Orban PC remote software that you have probably encountered with the Orban hardware processors. So you can control the server machine from elsewhere on your internet, or even over the internet if you use VPN. There's also a couple of levels of security built into the software, so you could even run more than one streaming provider, or I should say streaming client on one server machine. And it can be very cost effective. You can run up to 16 highly advanced audio processors on one computer with dual Xeon processors. Run up to 8 with inexpensive i7 hardware. This depends on whether you're using the MX limiter or not. If you're using a relatively low target loudness, like -16 to -20, then you don't even have to run the MX limiter, and you can probably get up to 12 instances on a 4 gigahertz 4-core i7. You can combine it with playout systems and streaming software like modulation indexes streams to create up to 16 integrated internet radio station blocks. All right, so that's the end of my formal presentation, and I'm going to bring the camera back up. Hopefully you can see me.
Yes, they can, Bob. And
we're going to now switch over to question and answer mode. And I'm just going to do that right now. Give me a... And you will notice a green hand that will appear. So if anyone has a question, please initiate the green hand and I'll see it pop up and we'll enable your microphones. All right. No. Any questions? Dave? Okay, let me try again. Here we have little difficulties with that. Let's see if we can try that again. Okay. Okay, here we go. Dave Rush. You have a question, Dave?
Yeah, I do. Just like to ask Bob to comment on the new flagship processor.
I can't really hear the question. I hear something very faint in the background.
Okay, Dave, let's try that again. Can you speak it a little louder? Can you hear that, Bob?
No, it's extremely quiet.
Okay.
Your volume is normal, Jane, but David's is almost non-existent.
Wow, that's a switch. Dave's your volume a little higher?
Can you hear David?
Okay.
David, is your microphone working, or are you accidentally being picked up from the microphone on your computer?
I'm not sure, David. Did you get that? Okay.
I'm just hearing a little bit. I'm hearing a little bit of codec burbling, and that's about it.
All right. Let me just try to take your voice back there.
Maybe David, you can text the question.
Okay.
My audio is somehow switching off on the microphone. What I was going to ask Bob is if he could comment on the new flagship 8700 and how it differs from the 8600 and what different features it has.
Okay, well, we will be introducing the 8700i at NAB this year, which is about 2 weeks away now. And in addition to the 8600, it has subharmonic synthesis. It has dual power supplies. It has the new Orban exponential loudness, which is a psychoacoustic process that was developed by the folks at basically the successor to Neural Audio, Robert Reams, who is quite an expert in the realm of psychoacoustics. And it's also going to have the ability to send a audio over IP stream to anywhere in the world so that you can actually listen to the sound of your processor remotely via MP3 or the Opus codecs. It's going to have built-in Dante audio over IP, and you'll have all of the important 8600 version 4 features in addition to that, such as the multi-path mitigator phase corrector.
Okay. Hopefully we answered that question for you, Dave. Any other questions? I'm going to try to switch this audio mode back to another mode and back, so bear with me because maybe there's a disconnection there. One moment, please. Let's put it on to listen only. Okay. And okay, I've just enabled the Q&A. Is there any other questions? And I'm going to try to get up. Any other questions? Okay, so to ask questions, you'll see a green hand that should appear underneath your video mode. And then you'd click on that, and that will indicate to me that somebody has a question, and I will enable your audio button. I can't tell. 1 second. I'm going to try to bring up if there's any other. Okay. Let me just switch the room settings around so we can put a bit of just switch this around a little bit to see if we have any questions in the chat box. Does anybody else trying to ask a question? Bob, I don't know if we have some technical difficulties here, but I'm not seeing any questions at this point. How about if you have any questions, I'll have you email me, and I'm going to follow up with the presentation with a video coverage of this present webinar, and my email will be on there. And if there's any other questions, we can ask Bob to handle them a little later and get back to you. Is that okay, Bob? That way we can address them. I just want to also do a quick mention that Bob and Orban will be at NAB booth N3203, and I hope that you'll have an opportunity to go there. And I'll be there, so if you want to set up an appointment through me with Orban, kindly let me know. Also, we have a quick survey. I just want to let people know if you have technical questions, you can click yes or email me, and we'll get someone from Orban to answer them or address them. And also, we have a trade-in situation with Orban products, old processors. If you want to upgrade or repair them, kindly let us know, and I'm going to follow up with an email on that as well. And before we close off, I just want to promote next week's webinar, which will be with Greg Olganowski, a former engineer at Orban, who now has his own company, StreamS, Modulation Index, and his program will be on Stream the Right Way over HTTP. Again, just look for my emails, and we'll make sure that you have an opportunity to register for that webinar. Bob, on behalf of CommSmart Canada, I thank you for joining us and for presenting today, and I thank all of you for joining us. And again, if you have any questions, just drop me an email, and my apologies for not having this work. It was working the last time we worked, so we'll figure this technology out. What can you do, Bob? Technology, eh? So anyway, thanks again, everybody, for joining in, and have a great afternoon.